So we're going to take Newton's law of motion, my dear friends, basically, and we'll be taking what we are going to do. We are going to take the concepts first, and after that, we will be taking the best of the questions which we can imagine and do a Newton's law of motion. They are going to be really helpful. So, my dear friends, here we go. The chapter starts with dynamics. We call it NLM, Newton's law of motion. Is it okay? Fine. So here we go. My dear friends, you definitely have idea what is Newton's first law, Newton's second law, Newton's third law. The basic problem which students face is that they somehow do not know the application part. They somehow do not know the application part. This is where they get entangled. And here we are. So what we are going to do is we are going to basically look at the application part, which are generally asked in AP questions. Fine, my dear. So I already dealt with this when I was taking class for Ishita. So now I take from very basics for Aditya. Aditya, could you please tell me the Newton's first law? What do you understand by Newton's first law? Inertia. And what is your understanding, basically? I would like to see where do you stand currently. That's what I want to do.
Okay, so Newton's first law of motion. It's just very basically saying that a object at rest will stay at rest, and an object in uniform motion will stay in uniform motion unless acted upon by an external force.
Okay. Unless acted upon by external force. Correct? Very good. And what do you understand by external force? There are two types of forces which we are going to deal.
An external force is like I would say like a force outside of the system.
Okay, good. So you are basically coming over there where I want to talk. What is system? Everything we will deal in detail. I believe I dealt with all these things, Ishita, when I was taking a system and all these things with you. You also be prepared, because if he is not able to prepare, I am going to ask you.
Okay, I'll try.
You have to try. You have to. Now I believe this is a testing time.
It's been a while, so I might.
The chapter is really interesting, first of all, and you will really enjoy doing this. That's going to be really beneficial. So now I start. Newton's first law, my dear friend. Very basics. Everyone knows that basically, but very few people actually know how to apply the concept. That's something which we are going to deal with. First law, Newton's first law. First law means I am dealing with obviously Newton's first law. First law says that it gives you a concept of equilibrium, which is very important. Now, what is equilibrium? Equilibrium means a body is at rest or a body is in constant velocity. I mean, how is that possible? Equilibrium means all the forces acting on the body is balancing each other. The overall force on the body is coming out to be, Ishita?
The total force of the entire, zero. Like they all cancel each other out.
Perfect. This is a mathematical way. This is basically the mathematical way to tell how we are going to deal with this one. First, the expression. You already know, I don't even need to write. A body at rest remains at rest, or a body in motion remains in motion until unless some external forces applied on it. If a body is at rest, that means I can show that velocity is 0. It remains at rest until unless some external force is applied on it. Or a body in motion remains in motion until unless some external force is applied which stops this body. Okay, my dear friends.
Yeah.
From here only we get the concept of external force. External force is defined something which is outside the system. Now what is system? System is something in which we are interested, in which the interactions are between which that, for example, two balls are there. We are interested in dealing with the velocities of two balls. They come close, they collide, they move away. I'm only interested in the velocities of these two balls. I'm not interested in any XYZ body. So basically, these two balls will constitute a system in which I'm going to deal with where two bodies are interacting with each other. That is more going to be our system. Obviously, in this world, every body has a force of interaction with other body. Definitely, even I told that you are sitting in Los Angeles.
Yeah.
Ishit is sitting in Berkeley. I am sitting in New Delhi. But despite of that, there is a force between us. Which is that force?
A gravitational force.
Yes, perfect. Basically, that's a gravitational force which is acting between us. Okay. So, but if I am dealing, but I'm not going to consider if I have to deal with, for example, if I consider myself as a body and there is another body, we are physical bodies, we are colliding with each other. So I am going to consider only myself and the other body as system. I won't include Ishita and Aditya in my system because basically they are not contributing. I am only interested in these two bodies, only the interaction between these two bodies. This is going to be my system. Any force which is acting from outside the system, that's going to be external force. Okay? So body at rest remains at rest until unless some external force is applied on it. Until unless some external force is applied on it, that means F external is going to be 0. Got it?
Yeah.
Either you don't need to write. You don't need to write. Everything I'm going to send you, and after the class, you can write so you put your full attention in the class. No one writes in our class. Basically, you simply just go ahead. F external is 0. If F external is 0, the body will remain at rest. A body remain in motion, and remain in motion means a body remains in constant motion. With the constant speed it is moving. A body moves with constant speed. It does not decelerate, it does not accelerate until and unless some external force is applied on it. Because if external force is applied, then the velocity will change. Got it, my dear? So basically, it's all a game of external force, my dear friends. A body now come to mathematical way in which we are going to deal. My dear friends, you know the first law. Let's come to the application part. This body is there, and we are going to actually make the free body diagram of this body. Can you please tell me what all forces are acting on this? I would like to know how much you know.
There's two forces acting on the box.
Yes.
There's a gravitational force, and then there's a normal force pushing upwards on the box by the table and the box.
Aditya,
Yeah.
I'm giving you controls. You can write on my board. Okay? You can write on my board. You please draw the lines, and I would like to see how do you draw, because those things matter a lot. Come on.
Wait 1 second. Draw with the same size this way.
Okay. You draw exactly. Draw everything exactly.
Everything exactly?
Yes, I'm talking about, it is a free body diagram. Okay? You draw everything exactly. That's what I want.
Do you want me to label these as well?
Yeah, I want you to label it, these as well. And from where should the line start? Everything means now it's going to be proper conceptual thing.
Okay, so and I mean that's about it.
Okay, good.
Or do you want me to explain Newton's third law?
Now, oh no, not third law. Don't do that.
Okay.
Don't do that. Now Ishita will make. Ishita will make. Come on. On the right one. Yeah, I would like to see how do you make. First of all, tell me what Aditya has made. Do you think it is correct?
I think it's mostly correct, but like, isn't it that like, sometimes the force is like if one of them points down, the other one points like from the side.
Tell me how to do.
Wait, but
Tell me. Come on.
And then like if this is the center.
Yeah.
Sometimes like I've seen it where they shoot.
Perfect.
Like people draw like just a little bit from the side. And pretend that's equal. Okay. That doesn't look equal in length, but it's supposed to be equal.
You both are wrong.
Okay, so
now I tell you, you both are wrong. Now I tell you reason. That's why I wanted to start everything from zero. Reason is because the basic concept clarity is not there. Guys, I want to tell you one thing. You have already studied Newton's law of motion. I am not saying that you guys have covered Newton's law of motion, momentum, work, power, energy, everything you have covered. But still, you are not able to solve the problem. Reason is the application part is not that good. You are not understanding the very basic concepts which are lying in solving these problems. Why do you do mistakes? The important thing. First of all, I would like to tell you one thing, my dear friends. Ishita has made mg, and you have also made this fg, Aditya, which is going to be mg. F and fn is the normal force. Okay, fn is the normal force acting. My dear friends, I tell you one thing. First of all, this normal force from where you are showing? You are showing from the center. You both are showing from the center. Do you think the normal force? Do you think the normal force occurs from the center?
No.
It doesn't occur from the center. My dear friends, come now. Let's use board. For example, I'm pushing this board. Okay, this board is there, and I'm pushing it. So this is like a board, and this is my hand. Okay, and I'm pushing it. The normal force occurs from the surface. It occurs from the surface. I am pushing it. This will also push back. I mean, obviously, this is a touch of Newton's third law I'm giving. I am mostly revising all the concepts. Which you have done. So don't say that, sir, this is a Newton's third law. Obviously, this is Newton's third law. You already know it. So basically, I'm going to revise each and everything in much more detail. My dear friends, I tell you one thing. This is not how you make the FBD. FBD is made in such a way so that forces what all forces are acting on the body. Acting on the body, not by the body. mg and normal force will occur from here. Got it? mg from the center of gravity, normal force from the surface. I want to ask you one more question. What is center of gravity? What is center of mass? Is there a difference between center of gravity and center of mass?
Like, I don't know. There's no difference.
Ishita.
I think there might be, but because center of mass is a concept that's in linear momentum, but our class hasn't talked about it yet. So
okay, so like center of mass is like where like it's like if you're holding a pencil, it's like a point where like you can balance it on your finger without it like falling over. It's like the point in which the mass is like at equilibrium.
No. The point at which the mass is supposed to be concentrated.
Yeah, and
okay, the mass is supposed to. And what is center of gravity? Then, if they are same, then why they are calling center of gravity and center of mass? They should be same.
Wow.
And you have studied Newton's law, and you are doing solving problems. So now I can understand how well you understood. Physics means you should know each and everything. You should question me, sir. Why? Why is this happening? See, a person who is teaching physics, a student of physics, he is a super logical person basically. Physics is one of the best. It is the best subject I have come across till now. I mean, not because I studied I did my master's in physics, but because physics makes you very logical. You start questioning each and everything. You want to know the reason behind each and everything. If somebody is saying gravity, if someone is saying mass, and someone says, okay, mg is acting from center of mass, you should say somewhere it is written center of gravity. You are saying center of mass. That means both are same. If both are same, then why there are two differences? Why two words have been made? My dear friends, center of gravity is the point from which gravitational force, the gravity, is supposed to act. Got it? What is gravity? Gravity is it's especially a force between a body and earth. Do you think that the force between you and me, it will be called gravity? No. It is just a gravitational force. Gravity is especially a term coined for force between body and earth. Got it?
Wait, can you? Okay. So
yeah.
Center of gravity is like the point at which like gravity like pulls on something. Is that like essentially what you're saying?
Yeah. So basically, I tell you one thing. I mean, these things you will understand when we will study gravitation. Gravitation, when we will be studying these things, the difference you will be feeling. Okay, why there is the center of mass is. First of all, you should have studied center of mass. What is center of mass? How to calculate? Then you should have studied what is center of gravity and how to calculate. Then you will see the difference. Gravity is the point. Gravity is the point. I make you diagram. It may happen that gravity, this is center of gravity and this is center of mass. It may happen. This is center of gravity and this is center of mass. They may not coincide, my dear friends. They may not coincide. Center of gravity, it depends on the intensity of the gravitational force. Okay? I tell you one thing, my dear friend. Now I tell you, as you move up from the surface of Earth, the gravitational force between you and Earth, it will keep on decreasing. You agree with me?
Yeah.
If you go far away, if you go in space, it diminishes.
It's
It
still
becomes
there.
zero. It's not there. Yeah. What I'm saying, it diminishes to zero. Got it?
Okay.
What is the value of 9.8? What is G on the surface? It is 9.8. G on the surface is 9.8. You know this thing? 9.8 meter per second square.
Yeah.
Ishita?
Yeah.
Is it okay? My dear friends, it is 9.8 meter per second square. But this 9.8 meter per second square, if you go like around, if you go around 3,000 or 4,000 kilometer away from the surface of Earth, this 9.8 will not remain 9.8. It will decrease. Got it?
Yeah.
Because as you go away from the surface, this G value, it keeps on decreasing. There is a formula for that also. I tell you how it decreases. G dash equal to G into 1 minus 2h by R. Height, h is the height from the surface. Got it? We will study all these things, but in gravitation. But at this moment, you should know that center of mass and center of gravity, they are not same. They are different. And why they are different? Right now, understand one thing, that it is because of the fact, because the value of G doesn't remain constant 9.8 throughout the space. It keeps on decreasing. When we deal with center of gravity, we are dealing with mg. Do you understand? It mass into G. So understand one thing, my dear friend, I want to tell you. Now develop a concept. This is a very big body. For example, a body is very big. It is ranging from the surface of Earth to 3,000, 4,000 kilometer. Okay? It is very big. A very big body, very, very big body is there. Okay? The mass which is near to the surface will be experiencing mg, which is m into 9.8. Agreed or not? Agreed or not? Fine?
No.
The mass which is near to the surface of Earth.
Oh, near to the surface of the Earth?
Yeah, I'm talking about the near to the surface of Earth. I'm talking about, you take a small molecule. You take a molecule, okay, or a bunch of molecules near to the surface of Earth. This is Earth. This is surface of Earth. Okay, they will be experiencing these particles, whatever their mass is, mass into G. They will be experiencing this force mg downward. Okay, yeah. The molecules which are far away from the Earth surface, they will be experiencing. They will also be experiencing mg, but that g is going to be different. That g is going to be g dash.
And how does this g dash change where the center of gravity is?
This g dash is this one.
Yeah, but like, how does that change where the center of gravity is?
We will discuss this thing in gravitation. When we will be discussing about gravitation, we will be discussing. I took this point so that I make you realize that, guys, center of gravity is not same as center of mass. Reason is, it depends on the mass remains same. The mass here of one molecule is same as the mass of other molecule on the top. But the force which are acting on these two molecules, they are different because of the fact the G value is decreasing as you are moving away from the surface. Are you getting it, my dear friends?
Yeah.
Center of mass, it depends on the mass concentration, density of the body. It depends how the mass is distributed. Center of gravity, it depends on how the force is acting on the different molecules, or I can say on the different particles of the body. Got it, my dear friends? So do not ever get confused that center of mass and center of gravity, I think it is same. No, my dear friends, they are different. One depends on the mass distribution, other depends on the force distribution. I believe these are the things which we are going to study in advanced level. Don't worry about all these things, but at this point, all these things are required. Come to the point, my dear friends. Come to the point. So basically, you have understood here and mg. We started from this point. And we have come to some different level. My dear friends, I want to ask you one thing. This first law you understood. You basically know everything, but application part I am going to take. What is Newton's second law?
Newton's second law is like
yes.
I mean, it's kind of hard to explain, but basically it's like all the forces acting on like a certain axis, if you add them all together, then you'll be able to get the total net force on that certain axis.
Now, Ishita will tell. Newton's second law, my dear friend.
I remember you explaining this to me because you said I don't know it conceptually, but I forgot. I kind of forgot what you said. But all I remember is like Newton's second law is simply F equals ma.
Oh.
That's all I can say confidently.
Okay. Oh, very confident. This is really, really awesome. So guys, first law, it deals with equilibrium. Okay. The equilibrium concept, it comes from the first law. I write it down also here. Equilibrium concept. The first law gives equilibrium concept. Equilibrium is summation of all the forces is coming out to be
0.
The equilibrium concept comes from this one. Summation of all the force, when this sigma, it is called summation. Do you know this one?
Yeah.
When all the forces acting on the body, summation of all the forces acting on the body, I write Fi. Now what is this I? I is like all the forces acting on the body. I can be F1, F2, F3, anything. Okay, equal to 0. Then it becomes equilibrium case. I give you one example. Don't worry about this one. The example I tell you. For example, my dear friends, this is the body. This is the body. This body is lying on the floor. Okay. One is pushing this body. One is pulling this body from here. One is pulling this body from here. One is pulling this body from here. F1, F2, F3. Okay, my dear friends, this body is not moving. Despite of the fact you guys are pulling this by F1, F2, and F3. Okay. I have not told that these are equal forces. I have not told they are lying 60 degrees from each other, like the angle between them is 60. They are acting in such a way, the forces are being acted by 3 different people. They are acting in such a way so that this body of mass m, it is not moving. Does it mean the force is not being acting on the body m? That's why it's not moving. Why this body is not moving? Can you please tell me? This body is still at rest. It is just enjoying over there.
Because the summation of all the forces, once you do vector addition, they'll equal 0.
That's what I wanted to hear. Very good. If you do the vector addition, it comes out to be 0. Do you know how to do vector addition, guys?
Yeah.
You resolve the force into components, I component and j component, if it is 2D, otherwise I, j, and k. That generally we deal with 2D only. At this stage, we are going to deal with 2D only. In I component and j component, you can resolve. Ishita, I told you this thing.
Yeah.
I told you this thing. So, for example, this is a body. If F is acting at angle theta, so tell me one thing. What is going to be this I component and what is going to be J component? Come on, my dear friends.
Like what is the I component equal to?
Yeah.
So it will equal to F cosine theta, the I component, and then the J component's F sine theta.
Perfect. Ishita, is it okay?
Yeah, I was gonna say that.
Is it okay? Okay, fine. Yeah. So this is basically this one. This ith component of this one is f cos theta, and this one is f sin theta. So I'm not going into much detail why this f it is coming out to be f cos theta. This is coming out to be f sin theta. This is more like this is very easy trigonometry. Okay, Ishita, I told you already, and Aditya, I believe you know this one already. If you do not know, you may let me know. I can. Okay.
If I know
believe
what
you know
now?
this term.
Wait, can you re-explain what you're saying?
You know this thing?
What thing? The vector addition? Yeah. Okay.
For this case, if you do the vector sum of f1, f2, and f3, it will come out to be 0. That's the reason the body is not moving. Okay. Come back. So let's discuss a bit about Newton's second law. That Newton's second law says that it actually gives the measure of the force which is acting on the body. Overall total measure of the force which is acting on the body. If we talk about that this body is there, total force which is acting on this body is something like this. I tell you, F1 like this, F2 like this. Okay, someone is pushing and someone is pulling this body. My dear friends, again you are going to take components. You are going to take, if I make theta here, and this is like phi. I give phi, theta and phi. Okay, so the component of this is going to be, I make in a different color. It is going to be like F1 sin theta. This one is going to be F1 cos theta. Okay, my dear, F1 cos theta. This one it's going to be, for this one it's going to be F2 cos phi, and in this direction it will be F2 sin phi. Is it okay, guys? Everything is okay. Basically, when I'm dealing with this one, totals, it actually deals with the summation of all the forces acting on the body, okay, is going to be equal to mass into acceleration. Got it?
Mm-hmm.
Mass into acceleration. Okay. Second law gives you, and this F is basically external force. Acceleration comes because of external force only, guys. Got it? Acceleration comes because of external force. Now I give you one very funny example. For example, you and your sibling, they are sitting in a car. Okay? They are sitting in a car. One sibling is pushing other sibling is pushing the first sibling. Okay? They are applying force on each other. Isn't it? They are applying force on each other. But by their forces, do you think the car is going to move?
No.
No. Why? Two siblings
Because
are there. They are applying force on each other. Ishita and her sister, they are fighting. One is snapping. Her sister snapped. Then they started using on legs and on those things. Everything happening. And they are thinking since they are applying forces, they do not know anything in physics. Okay, they are very crazy people. They don't know anything in physics, and they are thinking that okay, since the car there is some problem with the engine, so it's good that we apply force on each other. The car will start moving, but the car didn't start. The car didn't move. Why? Ishita, why the car didn't move?
Because like if you if you think of the car as like the object in like your system, in order for the car to move, like the external force has to be like outside the car, like pushing the car from the outside, but like we're in the inside, so like us hitting each other isn't applying any force to the car itself.
Perfect. That's what. So because it is considered as internal force. These are internal forces. Got it, my dear friends? These are internal forces. The acceleration will come only if someone from outside. Now then Ishita decides I come outside and start pushing this. That's what happens many times. That's what people used to do in old age. When the engine was not starting, they come out and they start pushing it. Then it used to start. Okay? So my dear friends, this is external force. Got it? This is external force. So what is system? We are interested. The system is basically car. Got it? System is car and what is there inside car. Agreed, Ishita?
Yeah.
I use a different color. That would be great. So now you are getting Aditya. What is system? Because I am only interested in this thing. I'm only interested in car and what is there in car. I'm not interested something with outside. I'm only interested with the motion of car. I'm only dealing with the motion of car. Are you getting?
yeah,
So do one thing, guys, for me. Since I told you that F external, sigma F external force, if I total the external force, that is the measure of all the forces will come out to be equal to mass into acceleration. Newton's second law gives measure of the force, measure of the external force. Got it? It doesn't talk about equilibrium and all. Equilibrium and all, it has already been talked about the first law. Newton's second law gives whatever force is equal to, and the body is moving. The body is moving with some acceleration. You are applying a force and a body is moving with a acceleration. The mass of the body is m. If you do not know the force value, you can say the force value is going to be mass into acceleration. Got it? So second law gives the measure of the force. So can you please write the expression for this block which I made F1 and F2 acting on theta and phi? Please try. Please write, and I want to see how it is. Consider that the body is moving on the right hand side with a acceleration. Come on, guys. Consider on the force. This is a body of mass m. Everyone, please.
I'm still doing it.
Make FBD.
Wait, it's just moving to the right?
Yeah, it's moving to the right. Okay. If you want, I can. My this one is not working. I don't know why. Just a moment. Okay, never mind. I tell you one thing. Okay, my stylus started working. It got. I was looking for driver. Uh, its battery got down. Now it has. Wait, I have to. Maybe. Okay. So, I mean, when I was teaching you, it became loose. So I was finding out what's the wrong. I tell you one thing, guys. I tell you. Okay. So
Yeah.
Yeah, here we go. So basically, obviously, this body will move towards right with acceleration. I can write here as F1 cos theta plus F2 cos phi equals to mass times acceleration, mass of the body into acceleration. Okay?
Yeah.
Summation of this force is going to be external force is going to be mass into acceleration. This is given by second law.
Yeah.
The body is not moving in vertical direction. It is only moving. This is the equation in x direction. This is equation in x direction. The body is not moving in y direction. That means it is not moving. It is at rest in y direction. That means this body is in equilibrium in y direction. That means summation of all the forces in the y direction should come out to be 0.
Yeah.
Got it, Ishita?
Yeah.
Isn't it, my dear friend? So basically, what all forces are acting? One force is mg. Okay, one force is normal reaction. On downward force, I can take any direction as positive, any direction as negative. But for you, since you guys have studied that upward is going to be taken as like plus j, and downward it will be taken as minus j. Okay, so better is you take the top upward as positive and downward as negative. Guys, I want to tell you one thing. I am not using I or j in this equation. That I am just writing a vector. I am just writing a scalar equation. I am not writing these with direction, but I can write as f1 cos theta I cap plus f2 cos phi I cap equal to m a I cap. I can write. But since I know everything I am writing in 1D only, one direction only, so I don't need to use I and j. Is it okay?
Yeah.
For y direction, I can write. Upward, I am taking as positive.
Okay.
So upward forces are normal reaction plus F2 sin phi minus mg. Okay, minus mg. Let me use minus mg minus f1 sin theta. It's going to be equal to what, Ishita?
0.
Perfect. Got it?
Yeah.
So now simple. If that means I can write n plus f2 sin phi equals to mg plus f1 sin theta. I can also in a standardized language I can write upward force equal to downward force.
Yeah.
Obviously, guys, upward force equal to downward force. When upward force is going to be equal to downward force, the body is not going to move in vertical direction.
Mm-hmm.
Agreed or not?
Yeah.
Yeah.
As simple as that. As simple as that. If a body, in case a body is not moving in left and right direction, that means left force equal to right force. You can simply equate even without writing. Just you add the left force, it should be equal to summation of all the right forces. Agreed? That's all. So basically, this was just a review of Newton's second law. Okay? Come to Newton's third law. I'm just reviewing it fastly. I'll take the application of all these together in questions. Okay? Do one thing. you can see my now you can see the recordings. Ishita, I already talked to Ishita. The recording which I sent in your account, you can see on those recordings. Now you will understand better. Okay. Newton's
Okay.
third law. My dear friend Aditya,
Yeah.
tell me Newton's third law. Come on.
So
I want
basically,
to hear.
it's describing the action and reaction pairs that happen in forces, like free body diagrams. So that one example where you were talking about your hand and how you're like pushing your hand against the board, and how you're exerting a force to the board, but the board is exerting a force back onto you, hence there's no movement. That's an example of Newton's third law. There's an action-reaction pair, and these action-reaction pairs, they have to be the same type of force. For example, although normal force and gravitational force cancel out each other, they're not action-reaction pairs since they're not the same type of force. And
Fine. Okay. So you know the basic idea you already have actually. It's not that you do not have the basic idea. Now come to me. I tell you. My dear friends. Ishita, would you like to say something? I taught you already.
It's like for every action, there's an equal and opposite reaction, and isn't it that the reaction has to be on the like system or like whatever the object is itself? Like it can't be on like if you're talking about like you pushing your hand on the board, the equal and opposite reaction has to be the board pushing the hand on your hand.
Yes.
It has to be on the same object, if that makes sense.
Action. No. Wait. Repeat the last thing. If you are pushing the board, then
Like
board is
if you're
pushing you.
like if your hands push like putting a force on the board, then the equal and opposite reaction has to come back on your hand.
Yeah. Okay. Perfect. Okay. I tell you the expression. For every action, there is an equal and opposite reaction.
Oh wait, isn't there like something unless acted upon by an external force or something?
No. Where is external force? On everything, it's
Okay.
action. It's not. I mean, external force. All these things that they come into picture when we talk about system, basically. Got it? So here we are for every action. For every action, there is an
equal reaction.
equal and opposite reaction.
Oh yeah.
Opposite reaction on for every action there is an equal and opposite reaction on two different bodies. This is very important, guys. Many students they do mistakes, and even after telling, they do mistakes. I mean, because the application part did not understand. Okay. Now I will tell you something very significant thing from this. Okay. Very significant role I will tell you. My dear friends, Aditya,
Yeah.
this you will have to tell me because Ishita already knows this one. In case Aditya is not able to tell, I will ask Ishita. Okay. Guys, that normal reaction concept basically comes from Newton's third law. which we have been using in the FBD just before, that actually comes from Newton's third law. I mean, that concept comes from Newton's third law. I was believing that you already knew Newton's third law, so I was using that FBD concept and all. FBD concept, basically it should be taught once you know everything. So now mind, I want to ask you, Aditya, make
Yeah.
the FBD of this one.
Including.
Already made it mg, okay,
Yeah.
and normal reaction. I want to ask you, Aditya, what, and for every action there is an equal and opposite reaction. That means forces exist in pairs. It means forces exist in pairs.
This wouldn't apply to gravity though, would it? Right?
Sorry?
The Newton's third law, like at least for this box equation, would it also apply to gravity?
Why
Like
not?
mg?
Yes.
Yes.
Every force in this world has a reaction pair. Anyone you can call action, anyone you can call reaction. It's not that first action is applied, then reaction occurs later. Both occur simultaneously only. They both occur simultaneously. Okay?
Okay.
So anyone you can call action, any other will be reaction. If you call first as reaction, other will be action. Forces exist in pairs, guys. Forces exist in pairs. So Aida, please tell me, what is the reaction pair of mg?
The reaction pair for mg
Yes.
would be from the center of gravity this way. And it'll be like, let's just say just mg and then this. And then there will also be another reaction pair with normal force.
Ishita will tell whether it is correct or not.
I don't think so. I think the reaction pair for mg's normal force.
What?
I think the pair is like mg and n.
The pair is mg and n. My dear friend, I already told you all these things before. Now you will say, oh, I forgot. Yes.
Yeah.
I'm pretty much sure you will say this one.
Yeah.
So you have to tell me all these things now.
But isn't if the block is pushing down on the ground, isn't the reaction pair that the ground is pushing back up on the block? Yeah, isn't that like what I just said?
Do you understand something? The
Like
reaction pair, if mg is acting downward, my dear friend.
Yeah,
Now
doesn't that
understand
mean
one thing. This mg is acted by Earth. Mg is acted by Earth on the body. Aditya.
Yeah.
The mg is acted by Earth on the body. So body must also be acting some force on Earth.
Wait, can you repeat that?
I am saying mg is acted by Earth on the body.
You're saying mg is acted on Earth by the body? Okay.
Both are correct basically. mg is acted by Earth on the body, and so the reaction pair is going to be bodies attracting the Earth by equal and opposite force, which is mg only. Equal but opposite in direction.
So
Earth
what
is
am I?
attracting body. Earth is attracting body by mg. So body will also be attracting Earth by mg, but they are going to be opposite in direction but equal in magnitude.
So isn't the thing I drew also correct?
No, that is not correct.
But
that is not correct. Reason I tell you, because the Earth is pushing, Earth is attracting, Earth is pulling the body towards itself with mg force. Okay.
Yeah.
Which is this mg force. This mg force is this one.
Yeah.
So body will also be pulling the earth towards itself with mg force.
Oh, it'll be pulling the Earth. It's not like, okay, so
Got a point or not?
wait, what?
Got a point? They
So
are.
okay, wait, let me draw the diagram. So you're saying like if this is Earth, right, and there's like a particle here,
Yes.
then there'll
Okay.
be like mg here,
Yes.
and then like all the way to the center of like this point, and then
Yes.
there'll be an mg this way, where the
Perfect.
particle,
Now
yeah,
you get it. That's what I am doing from the center, because we will understand one thing, that the force acts from the center of gravity. Earth, Earth and body, they are all symmetrical. We are considering the Earth to be like symmetrical only. So its center of gravity will coincide with the geographical center of the Earth. Got it? So
yeah,
on the forces will be acting from the center.
yeah.
On the
So
body also, the mg will be acting from the center of gravity. On Earth also, the force will be acting from the center of gravity. So if I consider this as action, this becomes reaction. Got it? If I consider this as action, then this becomes reaction. Got it?
yeah,
So these are action-reaction pair. But then what is N? Why is this coming?
where's n coming?
Yeah, why is this
What?
N coming?
Because there's another reaction pair for n.
What's that? Which one is that?
But isn't it separate from these because it's a different type of force?
Okay, understood. So N and Mg, they are not the action-reaction pair. Many
Yeah.
of the students, they do this mistake, that N and Mg, they are action-reaction pair. My dear friends, they are not the action-reaction pair. Understand one thing very deeply. N is coming into picture. N is normal reaction, is basically a resistance to the penetration. What did I say? Resistance to the penetration. Now, what is this resistance to the penetration? I write it down for you guys. Okay, what it is? Resistance to the penetration. Resistance to the penetration. See, my dear friend, I tell you one thing. For example, if Earth's surface would not have been there, then this body might have fallen down. Agreed or not?
If there was what?
If there were no Earth's surface, then this body must have fallen down. It must have gone inside.
Yeah.
So, for example, this mobile phone is lying on my hand. If
Yeah.
the hand is not there, it will fall down.
Yeah.
Isn't it? That means the tendency of the body is to go down because of mg only. But this Earth's surface is resisting the body not to come inside it. It is resisting. Hey, please don't come inside me. It is resisting. Go out, go out, go out. Got it? Got a point?
Mm-hmm.
That resistance to the penetration is normal reaction, and it occurs from the surface. Normal reactions, they are applied from the surface.
Okay.
Got a point? So many of the students, they do mistake that they consider the Mg and N are the action-reaction pair. They are not. N is coming as a result of N is coming because of Mg acting on the body. It is trying to go towards the center of Earth, but the surface of Earth is resisting the body. It is pushing the body out. Hey, please do not come inside me. So
Yeah.
it is coming because of that. That normal reaction is coming basically because of that. Got it? My dear friend, Earth is pushing the body with normal reaction. So body must also be pushing the Earth with the equal force in opposite direction.
Yeah.
So the reaction pair of normal reaction is going to be this one. These are the action-reaction pair. Got it? Anyone you can call action, anyone you can call reaction. That's not a big problem. Action-reaction pair. It can also be treated like this. You consider, guys. You consider one thing. It can also be treated like this. That that the Earth wants to penetrate. Earth wants to penetrate inside the body. Earth wants to penetrate inside the body. Imagine. Reason, because body is pulling the Earth by mg upward.
Yeah. So you can think about it both ways.
So we can think in reverse direction that Earth wants to penetrate inside the body, but body is not allowing the Earth to penetrate. It is pushing down. Hey, please do not come inside me. I don't want you. Got it?
Yeah.
So that is coming because of this one. So this action-reaction pair of normal reaction, they are acting on different bodies. And always understand one thing, action and reaction pair, they act on different bodies, not on the same body. The biggest mistake students do is they consider the Mg and N, they are action-reaction pair. Guys, action-reaction pair, they act on different bodies. I write it down for you once again. I write it down for you. Don't worry about this one. Action-reaction pair act on different bodies, not on same body. N and Mg both are acting on the same body. So how can they be action-reaction pair? Understood?
Yeah.
This is how we understand this one, my dear friends. Act on different bodies, and I specifically mention not on same body. Though it means same only, but still I am writing not on same body. Agree?
Yeah.
So this is the thing, guys. Ishita, are you able to revise something?
Yeah.
All these things I told you or not? Got a point? So these are the basic things, guys. These are the basic things which we wanted to cover. So this is all. This is all we wanted to cover. So this is more like a little bit of revision of your concepts. So Aditya, did you understand some new things today?
Yeah.
What all?
Like, what are those new things? Like,
which you didn't study in your school.
that it was about Newton's first law. It was like wait, no, wait. I had a big misconception about it, and then let me think about it.
What was the misconception?
I think it was. Wait, can I move around the notes? I remember looking at it, and I didn't write it down because you told me that.
Okay, move it. You can move it also.
I think it's up here. Oh yeah. So when you're talking about Newton's first law and you're talking about equilibrium, and then you told me to draw the force body diagram for the box lying on the table. I drew it, and then you explained to me why I was wrong. And then I thought it was weird because I've been drawing all my diagrams like that, and my teacher has just been like, it's fine. And then the way you explained it after, like the one in red, that one box, it makes sense because that's where the normal force is being acted upon, and it also explains where the gravitational force is like where it's directly being pulled. And I thought that was like kind of interesting because it doesn't show like the how would I say it? It's like it's more precise like way of describing the forces acting on the box, and I would have never drawn my force body diagrams any other way other than how I was doing it before until this lesson.
I tell you one thing. One thing. In many of the generally in the FBD, they are drawn like this. They consider the whole body as a point. They consider the whole body as a point, and on that point, they show the forces. like mg and normal reaction. Got it?
Yeah, that's why I drew like a little point. Yeah.
Basically, they draw like this. But while doing question, I believe these are more conceptual way. This is in case they want to show it. In case they want to show the only the forces which are acting on the body, it is okay. But this is in much detail we are making these things. Normal reaction acting from the surface, mg acting from the center. Got a point? And in case friction acts, now friction will also come into picture, we will consider it. So friction will act from the surface. Got a point? It not from the surface. The friction will act like this. You won't show friction from here. This is going to be wrong. Got a point?
Yeah.
So from where that force is occurring, that also we show. Though generally the concept of FBD came from the idea that you will consider the whole body as a point and you will show only the forces on the point. But this is a detailed way. Nowadays we do not consider like this. We simply make the block and do the questions. That gives a better idea. We consider this as also FBD, and obviously this basic concept. No one makes FBD like this. Only if someone is specifically asking the question that, okay, make the FBD, then you will consider the body as a point and make the FBD. Otherwise, don't make body as a point. I would say, just keep the body as body and do the question. Okay, so and you understood one other thing, that equilibrium concept, Newton's second law. It gives some measure of it. Newton's second law. It gives measure of. I write it down for you so that it becomes. It gives. I write it down for you. Ishita, what are you sketching?
Nothing.
It gives measure of external force. It gives measure of external force, my dear friends. And Newton's third law basically talked about that for every action there is an equal and opposite reaction. But conceptually we understood one thing, that the action reaction did act on different bodies, not on the same body. Okay, these are really important things which we need to understand, because without these things we will be able to do the question. I am not saying that you won't be able to do the questions, guys, but you will be doing only incorrectly. Got it?
Yeah.
So these are the things. I think now we can wind up this class, the conceptual class. Tomorrow class we will be taking only questions, the application part. Okay.
Right.
So
Wait,
if you have any
class tomorrow?
yeah,
Oh.
same time, 9 p.m.
Okay.
PST. 9 p.m. PST. That is 10:30 a.m. IST in Los Angeles and Berkeley. I think the times are same.
No,
only.
it's the same. Yeah.
Yeah.
It's same. So that's in fact benefit only, and I think 9 o'clock is good. So tomorrow you can come up with now you can start doing some questions. See the questions how they have been done. We will be taking some questions. I have revised this one in a faster way. Reason, because you have already studied all these things. I taught Ishita, and I sent videos to Aditya. So my focus will be on doing questions now. This would help you a lot. And if you have some questions already, guys, which are there in the book, which you feel tough, you can send me on WhatsApp. Okay. I will look at those questions. And if you have even some papers which you have done earlier, but you did it wrongly and you want to understand, that also you can send me. Send before the class, so that I can just look at those, where you are doing mistake, where you must be doing mistake. You can send in the morning time itself. Okay. So should I stop the class now?
Yeah, I think we're fine.
Okay. Sure. So I stop the recording.